Hello, guys. This is Masfan speaking. Today, I would like to run a hydrologic model, HEC-HMS model, with the same data that I used some months ago. I just designed manually a reservoir, and I did reservoir routing manually. Today I would like to use the same data to analyze using the software HEC-HMS and see the difference between manual calculation and using a software. What will be the advantage, or how we do it easily using a software without calculating, thinking about developing a storage indication curve using Excel sheets and so on. And instead of that, we just simply use a software and put the data into the software and run it, analyze, and how we can do that using HEC-HMS. That's all. You can see from my previous video that I did, we can see that here, see, just to start from the very beginning, exact design procedure. Here is the design that I did before, and the idea was, if whenever we construct a new village, or whenever we modify an area or a catchment, a watershed, maybe doing asphalting or building houses and so on, we change the runoff behavior of the soil or the area, the catchment. So definitely the runoff will increase when we do lots of asphalt and so on, or concreting the land, or compacting the land. So somewhat the downstream side of the area will be affected. I mean, the discharge will increase, the runoff increase, discharge increase, and the peak increase. So most of the time, the downstream side structures, culvert and so on needs to be readjusted, or the water that is coming, because it is designed for the previous discharge. So either we have to increase, redesign it, or we have to reduce the discharge into the status quo, into the previous discharge and peak flow. How we can do this? Just we develop a temporary detention reservoir, something like that. But the procedure we are going to use is just simply a reservoir routing that is going to be used to calculate the hydrograph for any dam, any reservoir, big dam or small dam, anything similar. It's just the scale might be different, but the procedure is the same. So that is it. The calculation I did before manually is indicated in the video that I did before. It is available online. You can check that. We can see this is just simply a reservoir. It's just a model, just to indicate that it's a reservoir with an orifice and then a weir structure. Well, this is a weir and this is orifice. And there were some hydrologic calculations here, hydraulic calculations, orifice formula used here, and also calculated storage, discharge, elevation, storage curve. I developed that, and then after that I developed a storage indication curve. Then later I use that storage indication curve to calculate the outflow hydrograph. So we can see that here is just simply just to show you you can see it by yourself. It's available online. Yeah, this is the discharge storage indication curve. Before that, I have developed two discharges, two curves, elevation discharge curve, and also this is the hydrograph, the given hydrograph. Let's see. So sorry. This is the elevation storage curve. Before that, there is a hydrograph. This is a given hydrograph which I use to calculate the outflow hydrograph. That is the coming flow. So for the coming flow, we have to design a reservoir, and that reservoir release the water slowly, and the outflow hydrograph must be less. The peak discharge must be lower than this one, must be attenuated, and there should be some lag time also, a gap between, so that is the advantage. It reduces the peak flow. At the same time, it also the lag time also increases, so we will have a certain period to release the water to the downstream side. That was the idea. So here are the curves that I developed, and the final result was this one. The final result, you see, the elevation, the outflow discharge was 0.3 meter cube per second. I calculated in the maximum elevation that the reservoir has. The level of the crust level, the outflow, was 32, 0.4. Because there is also an orifice here. So that is it. That is the crust level. That is the design. You see, the advantage of using the software is many. It has multiple advantages. It means that here we just simply calculate a hydrograph and to know, for example, the water that is discharged, we have to calculate the area below the outflow hydrograph. That is the water that is discharged, and the water that is stored in the reservoir is calculated from the area here. The area. This indicate or tell us that the stored water quantity, volume, is this one. That is how we calculate manually. You need to calculate, let's say, area, something like that. But the software, the HEC-HMS software, calculates for us automatically everything, every detail. After calculating the hydrograph like this, also tell us the storage, the water that is discharged, the remaining water, and the level of the pool at its maximum discharge. When the outflow is maximum, what is the pool level? That's also indicated. So it has some advantage, actually. It has advantage, and also it facilitates, the process. It makes easier, to calculate. While calculating by hand, it takes time, and it needs concentration, to calculate. It follows the procedures and know each and everything. and understand also what we are doing, while we are calculating using some mathematical formulas. But the software doesn't need that one. Just simply put the data. As long as you know how to put all the data, then it will be very, just simply run it, simulate it, and find out the result. The purpose of this video is also the same. We have done it, manually. You can, if you want to study how even the software calculates it, it's better to see able to calculate manually first, understand the process, then do it with the software. That is the aim of this video. Okay, we can start the HEC model, for example. What is this? Okay, this is the HEC model. HEC-HMS model. First of all, we have to create a new project. That project means the reservoir model. Well, the method is called modified pulse method. The methodology, modified pulse method. We can call it that way. Reservoir, for me it is reservoir design. Let us call it the project reservoir design. That is it. Great. That's the reservoir design. We have to now develop a model. That's how we can basic model. You see a new basic model. It's a basic model. How the process, how it is going to run for us. Something we have to inform it. That is the basic model. Now, basic model. You see, the basic model needs to have all the schematic representation of the process. Yes. For example, we have an inflow hydrograph. So we have a source. It means the source is this one. Source creation. First, we have to create the water. This is inflow hydrograph. It's inflow hydrograph. When, let us say it is inflow hydrograph. Okay, that is the source. Then you see we have already created the source, and the water that is coming enters into a reservoir. That is the reservoir one. That is the reservoir. Then after the reservoir, it goes out, and there should be some kind of sink. They call a sink that collects all the water that is coming. That is just assume that this is for the outflow hydrograph. That is a sink. A sink is necessary, they say. So these are the three schematic records, and we have to connect them. To connect them, we have to go there to the inflow. In the inflow, the downstream is the reservoir, and the sink, and for the reservoir, the downstream is the sink. So now they are connected. It means the software is going to understand what we are going to do. You see, so the software is going to understand what we are going to do. This is it. It's connected. Now the next step is we have data. The inflow data must be entered. The storage discharge curve. See, first the time series data, that is discharge data, flow data. we have to, this is gauge the data, gauge the data, or just simply inflow hydrograph, inflow hydrograph. That is the time series data. You see, we have time series data. Here it is. It's discharge gauge time. That is it. Now we have that. So we have developed already the stage, the storage discharge, and the elevation storage curve. So we have to also put that also here. For example, storage discharge, storage versus discharge. We can say storage versus discharge curve. That is, the other is elevation storage function curve. That is elevation versus storage curve. These are very important two curves, you know. This is a curve, this is the other curve. Elevation storage, elevation discharge curve. So now we have stream data, time series data, elevation and storage curve, and also we need to put some meteorological data, because the Met 1, you see, the software assumes that there is a meteorological data, and it wants to tries to pick some information, so we need to give that information. If there is no any meteorological data, we say yes, we don't have a meteorological data, so that the software will understand that yes, this base model, yes, that is it, that is the base model. Everything we are going to do is total overrides. No, this is specified graph. Hydrograph is specified already. You see that is default specified hydrograph. No, we don't need this hydrograph. So that is it. We have, you know, that is the advantage of having a MET, because we inform there is no hydro-specific hydrograph or something like that. And also we need some control, you see. Control one, assume that it's control. So that the control always contains the time series, this similar with this one. So the time series must be readjusted, because our file indicates that here the time series hydrographic data here, you see. This is it, 10 minutes time step, and the discharge, entering discharge is this one. So we have to copy this, and this is here we have to correct here. 15 minutes is not 15 minutes, it's 10 minutes. It's manual, it's keep per second units can be. Time 00. Okay, the total time is 210 minutes. It means 3 hours and 30 minutes. So that is it. The day is 1 day hydrograph. That is 2021, we can say, although this is not important. You see, that is it. The table is here. Now we can paste it. You see, all the data for the hydrograph in 10 minutes time step is already entered. This is the hydrograph. This is the given original recorded hydrograph. That is it. So the control must have the same with this one. This one Okay, control, we can go here, control, this is 0, 0, 0, 0, and 0, 3, that is something, that is it, and it must be 15 minutes. Okay, that is a control. Now the storage discharge curve, this must be this one, and also here is a table, we have to fill this table. Similarly, we just bring that storage data, that is the storage which we calculated using that formula, you see, area conic formula, the storage will be at this level, this resource, then the cumulative storage is given here. But because the data there is, I mean, in the software, it multiplied. No, this is not one. This is the old one, I think. Okay, you see, here it is 1,000 meter cube. So that one is not in 1,000 meter cube. It is just in meter cube. So we have to adjust that also. To adjust that, we simply divided our data with 1,000. You see, just simply divide this one with 1,000. Yes, here you see, that is divided by 1,000 to just here we see, to make according to the need of the software, you see. So this is the discharge. We have to go there to bring the discharge also. That is the discharge. The discharge is calculated from the, from that weir formula, orifice. Here is, yeah, you can see the previous video, how I calculated all this discharge, but now we can simply take the data and paste it here. It is a meter cube per second. That is it. That is the graph. We can see. You see, our graph is just storage elevation, so it's just turn it down because of the axis changes. That's all. But it is the same curve. If the discharge were here, the curve will be like this. Like this. It goes up and down. So that's it. That's storage versus discharge. And this one, elevation versus storage. The same thing, we are going to bring the elevation from the storage is the same. You see, this is the elevation. This is the elevation. We bring that elevation here, paste it. Shit. No, I made a mistake. Copy, paste it. That's it. The storage, we can go again. This is the storage. So here is the storage. That's all. The storage is done. That is the storage elevation curve. Similarly, the elevation is the storage. The axes are different that we used. They inversed it here. It is different in my calculation, manual calculation, but the same. That is just simply the axis is changed, but the result is the same, similar. So that is it. That is all the data we need to calculate, to do the reservoir routing. Everything is done here. So here is the inflow graph. Flow method, that is discharge gauge, that is the major discharge gauge. inflow discharge gauges, inflow hydrograph, reduction. Observable flow is that inflow hydrograph. As the data it needs to, and they said that the outflow curve method is the one which use the modified pulse method, so we have to put it here. Outflow curve, I learned that. And this is the elevation storage discharge, and this is already given storage discharge, that is the one which we did. Here, this is also elevation storage, the one we did. So here, the primary elevation, because we have the elevation, we know the elevation, so elevation storage. Elevation storage can be the primary, so that we can get these values here, so we can choose elevation. Initial elevation is 3048. Initial elevation, I mean the surface of the floor of the, I think 3048, the floor of the, as I understand it, that is 48. It is the minimum level elevation, 30 above. Yeah, 30 means it is above the benchmark or any reference. Maybe the benchmark is 0 and that is it. Whatever it is, maybe it is above sea level. Yeah, someone have asked me that. That's how it comes 30 meters big. No, that's just a reference elevation. It means there is a benchmark that is 0 above that 30 meters. It doesn't tell any, it's not the height of the reservoir or something like that. It's just an elevation. Maybe that is above sea level as well. So anything calculated above this 30, 48, whatever, it can be 2 meters, 3 meters, then the elevation will goes up accordingly. If, for example, if it becomes 32, that means it is almost 2 meters or 150. That must be considered. That must not be confusion here. So that is it. That is everything we need. Observable outflow is no. There is no observable outflow. We don't know observable outflow. So the sink, I think, doesn't need anything. I think observable flow here, inflow hydrograph is not necessary here. I think so. If it is necessary, I'm going to adjust it, but it's not necessary. So everything is done, so we can save it now. Project must be saved, and we can run it now. So we can create compute simulation. This is run, finish. Now you see the computation is already here. We have done it, and now the result we have to simulation compute. We have to run this one. Compute, run this one. Now you see simulated result is now you see inflow hydrograph. You can see this is a given one, but you see that is it. Another one, that is the inflow hydrograph. That is the summary table. The peak discharges 0.6, volume of water, total volume of water calculated for us. The reservoir, the total volume, that is the incoming water from this hydrograph, is 2.5 or 2,500 meter cube. You see peak discharge, volume, standard deviation was percentage. Everything is calculated, time series. This has all, you see, the peak is 0.6, discharge or observed flow. This is observed flow. At 40 and 50, this is the maximum. Yes, that's the time, that's the date. That's what we get, That is outflow. This is the outflow. It's not correct, I think. There is a mistake here. The reservoir, that is the most interesting part. This one is the reservoir. See, everything, the inflow and outflow is indicated here. The maximum outflow here, you can see here, the maximum is 29, 0.3, which occurs here. Just that is at the cross point, the inflow equals the outflow. Inflow is equal to outflow. That is the maximum storage. When the coming water goes out, it means that is full. It can't contain more than that. This is the cross point is that indicates the maximum storage value reservoir. That means 2.5 maybe. Is that 2.5? No, that's not 2.5. It is here, 1.4, 1.5 almost here. You can see here. So you can see. Oh, that is 1 point storage, 1.5. When we can say 1,500 meter cube is the maximum storage, and the level of that storage is 32 something, 32.04. We calculated manually. Here 32.1. That's very interesting. So now we know the volume, we know the outflow hydrograph. We don't need to calculate it by hand, say the area, to know how much is stored, how much water is stored in the reservoir, and how much water is discharged out. Is also calculated from here, but we don't need that because the software itself summarizes everything for us, you see. Peak inflow, peak discharge, inflow volume, discharge volume, the one which goes out from peak flow, timing, that's the incoming peak flow. The peak discharge, that is the outflow. The outflow, you see, the attenuation, that is the lag time. The time between two is called the lag time. Peak discharge, peak storage, the peak storage is 1.5. And the peak elevation is known now. The crust level is known 32.1. So now, this is the hydrological design. And now, when we construct a dam, then the crust level should be 32 to store the water that is coming in, the available water that is coming in. It's a mini reservoir. We can see 1.5 meter cube is not such a big reservoir, or 1,500 meter cube is not. But it's the same procedure for a big dam also. Million meter cube of water stored, and the calculation is the same. This is the procedure. We calculate the amount of water that is going to be stored in the dam and the water that is going to be discharged. And we need also the elevation of the dam. We now determine the elevation. The dam height must be this. So that's all. And because we know the peak discharge, we can also calculate the length of the weir, the sluice, the gates. everything, the gate must be designed to accommodate the discharge. So that is that is the advantage of hydrology, and that's all the information we need. And also the information, for example, is very, very nice to report for. I mean, to do a report, we need all these informations. It is very easy to show to anyone who is going to read the report. Doesn't need to calculate or know, all the calculation steps. Just simply, he can easily see the storage water, how much water we are going to have, everything. Maybe the structural engineer doesn't need to know all the procedures, how time series, all the hydrologic data, and so on and so on. It's not necessary for him to know, but he needs how much water is going to come. The hydraulic engineer or the structural engineer or any engineer who is going to build the dam and doesn't need every detailed calculation. He just only want to know some important points, salient points, and use them for his calculation. You see, that is it. That is the advantage of having all information summarized in one report. And that is the advantage of HEC-HMS. You see, it seems very simple, but it is very important software to design a big dam that we are going to spend millions of dollars, and also we are going to harvest millions of meter cube of water. Water is dangerous, There is always seepage. A lot of things happen. You can't be sure. It's very difficult to completely stop even water. There is always a creep, seepage, and so on. So you have to recognize every consequences to take all the responsibilities, to construct a big dam. So this is very important, and I am happy that I am able to run this model. Apart from just I can calculate it manually, but that is tiresome, and it needs some concentration and so on. This one is perfect. And also, even if you can do it manually, this will confirm for you that your answers are correct. They are right. So it's very nice to have this software and use it if you can. That's wonderful. Merci beaucoup for listening. Thank you very much. That's all.